Welcome to the Green Chemistry 101 training series, produced by the Western Sustainability and Pollution Prevention Network. The course content for these videos was provided by the American Chemical Society Green Chemistry Institute, whose mission is to catalyze and enable the implementation of green chemistry and engineering throughout the global chemical enterprise. Other sponsors include the National Pollution Prevention Roundtable and the Washington State Department of Ecology.
Time to get real. How many of you do real-time analysis? Oh, we have at least two. Good. How many of you practice analytical chemistry on a regular basis? Okay, so that's good too. Good. So this is one of the principles, along with the next one we're talking about, that in my opinion are in the hopper of the forgotten principles. So I'm really looking forward to bring out some ideas. It's a forgotten principle because, again, in traditional synthetic organic chemistry, there's a distinction drawn between those who make the molecules and those who do the process chemistry. There's a big dividing line. And process analytical chemistry, by definition, is usually done only for process development. It should be done everywhere because, again, from understanding the kinetics of a reaction and you're doing synthetic organic chemistry, you really should understand mechanistically what's happening. But usually that happens much later in the development of a compound. We're going to talk a little bit about some of the methodologies of interest and some real-time examples and then some final thoughts. So, interesting principle, analytical methodologies need to be further developed to allow real-time monitoring so that we can control hazardous substance generation. Again, this principle, in my opinion, doesn't go far enough because it isn't just about hazardous molecule or hazardous substance generation. It really is about optimizing the chemistry and the chemical process. And if you don't have that real-time capability, you can't possibly optimize your process. So hopefully you'll understand how important this is. Hopefully you'll be able to think about some techniques that you can use and how you can use it to green your reactions. So this is really what modern chemistry tries to do. You take it from the laboratory and you just make it bigger. Okay, that's essentially what most people do. And process development really is a combination of this basic chemistry optimization, which again, academically, this is where most people spend their time. If you are an engineer, chemical engineering, you're really into performance efficiency and cost in your process development. This is considered to be a very highly specialized area, this technology, analytical tools, and engineering. And then finally, very much at the bottom is the regulatory EHS and green chemistry. So when we think about a process and process development, again, we think about things like reactors. And reactor sizes make a huge difference in terms of both mass and heat or energy transfer. There is a concept about reactor numbers we'll get to later on, whether or not we run it as a batch process. Most of what you're familiar with is batch processes. I doubt, I shouldn't assume. How many of you regularly do continuous processing? Okay, so there's one. So most of what gets done academically is batch processing. That's what you're most used to, occasionally semi-batch. And occasionally you do things like temperature and pressure. pH many times is important, but the order of addition and that kind of thing isn't so much. These kinds of things you're all familiar with and all very interested in yield and conversion, but some of these other things like how much heat output am I doing? What's my load? Again, if you're a chemical engineer, you talk about thermal load, but not if you're a chemist. Kinetics only comes much later when you're interested, again, in mechanistic type things, but that should be something you do routinely. What is the order of the reaction that I'm doing? Typically, we always go to the round bottom flask, or in a industrial setting, it's a 100-liter reactor or a 10-liter reactor, and it's a standard reactor type. Very rarely do we play around early in the game with different kinds of reactors. And trust me, when it comes to industry, they use all kinds of reactors. So this notion that you just have one option is kind of crazy. You really should be investigating the reactor or the reaction space as much as you're investigating the synthetic design. So what analytical chemistry and real-time analysis will enable you to do is things like parallel synthesis, bench pilot scale reactors, and adiabatic reactors. Apply to all those things and get lots of information simultaneously. Semi-batch chemistry, again, most common. Automated liquid feeds industrially, temperature control. Distillation is you usually have distillation overhead columns that are part of the reactor, and they're used quite a bit. You can do that, and that's what it looks like in the lab. I don't know how many people have these kinds of setups. You'll see that in industry quite a bit. The pilot scale, again, move up to maybe a 20-liter reactor. You get a little bit more challenges in terms of the design. Then you get into safety considerations, and so we'll talk a lot more about safety considerations in the next talk. And pilot scale, so multiple reactors. This notion that we do multiple reactors in parallel is not something that we typically do. Normally in scale up, we do not number up, we scale up. We just increase mass and volume. In the future, I would say you ought to really consider numbering up as opposed to scaling up in mass and volume. That is, you use lots of smaller reactors to get to the volumes that you ultimately want to get to. And that's just an example of it. And then finally, robotic screening. Again, I don't know how many people do this. If they're doing massively parallel synthesis and developing huge libraries to challenge and development, it's mostly a medicinal chemistry type tool or agrochemical development. It's used more in solid state chemistry these days to develop ceramics and things like that and high throughput screening, but it's generally not a tool. It's fairly expensive, but it actually is very highly automated. You set the reactions up and they run off and create your analogs on the order of scales of millions of compounds a year. And that sort of gives you an idea of what it looks like. So in process chemistry, we can shrink our reactors, we can number them up, but what else do we need to optimize the process? And so let's think about that a little bit. Real-time analysis, again, I said, is typically not something that you're taught. It's not something that you do in your research work as a graduate student, but it ought to be. It can be used in virtually every part of your process development or your route development, from screening all the way through to product development. And there are different kinds of techniques that you will use depending on which one of these that you're using. So, like so many other things, it's asking the right questions when we approach this. What kind of instruments, for what level of screening, for what level of process development do I need to have? And the instrumentation, the palette of instrumentation needs will change as you develop your process. Where do you measure? Do you measure continuously? Do you measure at discrete intervals? How do you do this? And it's really important to think about things like that. And then finally, I made that plea earlier on about design of experiment. And real-time analysis allows you to do design of experiment automatically or in a much more automated fashion. And the value is to create these models. And these models enable us, again, to optimize the process, to get kinetics information, to enable us to understand mechanistically what's actually happening. And again, I'd like everyone to walk away today with this notion or idea that understanding our reactions, understanding what's actually happening is absolutely key if we're going to transition from where we are right now. Because most chemistry, derisively described as bucket chemistry, has got to change. All right? The days of just throwing a bunch of stuff into a reactor and seeing what happens really need to be over. So these are the kinds of analytical methodologies that we use routinely. I'm sure that when the reaction is over, many of you use some kind of chromatography. Many of you will use mass spec or NMR. But you won't do real-time mass spec. You won't do real-time FTIR or near IR. And again, these are techniques that you ought to use. Occasionally, people get into some of these more esoteric forms of analytical instrumentation. Lots of reasons why we use each one of these. Again, spectroscopy is something that's non-destructive. Chromatography allows us to get into selectivity. It's relatively slow, but it has a wider dynamic range, so that's why we like to use it. Mass spec, highly selective. It's a little bit higher order of magnitude of difficulty to use it in real time, but it can be done. It is done routinely. Just a table to show you all the different techniques and where you might be able to use it. So real-time data acquisition is important because it tells us the story of what's happening in the reactor in real time. That's what we want. We want to have that level of knowledge and control over what we're doing. Many times when you follow a reaction, you actually can find out what's happening. Molecules move through transition states, which you miss, and which are actually the cause of byproduct formation. And if you're not doing that, then you're playing a guessing game as to why that byproduct is actually forming. So again, this gives us a window into our reaction. That's why we like to use them. Again, shortening development time industrially is key because time is money. And again, these techniques allow us to do and understand our reactions much better. Multivariate statistical process control. So anyone know what that is? Just raise your hand. Yes, no. So one or two people. Again, this is where we need to get to. That is that you know your process so well and you know how that reaction is occurring, and you can repeat that reaction within a statistical level of certainty over and over again. You can only do this if you understand what's actually happening. And again, in industry, this has been done, petrochemical industry, really since, I don't know, probably the 50s and 60s in certain processes. But in batch chemistry, this is very rare to have that level of control over what's actually happening. And you know, this is one of the things about pharmaceuticals is despite the fact that they're extremely well controlled reactions, there's very few people that even to this day are running real-time analysis of what's happening in a pharmaceutical reaction. And the FDA, Food and Drug Administration, is actually trying to push manufacturers to do more of this in terms of process analytical technologies. There are a lot of advances that are making real-time analysis more able to be done. And these are the kinds of things. Huge advances in electro-optics, doing changes in engineered materials, miniaturization, hugely important. The ability to collect and process data in real time was something that certainly when I was going through grad school, you could not buy a board and a PC and follow a reaction. It was always after the reaction was done. Nowadays, that's something that anyone can do. So the computing power is pretty awesome. This is a great example of miniaturization. And so you have a pre-concentrator thermal desorber, which is smaller than the size of a dime, and you have a 1 meter gas chromatography column. This, again, allows us to do real-time analysis in a way that couldn't be done before. That is analytical instrumentation on a chip. And it's just another example of that. Micro NMR. So you all, I am sure, have used NMR over again, and you take the tube. Very rarely, if ever, are you doing that on a continuous basis, and very rarely are you doing NMR on a micro basis. But again, this is something that is really a way of the future. So, monitoring of Grignard reaction, standard Grignard reaction, using medium infrared. Again, what that tells us, time, again, can't read German, and the IR signal, and we know that we're dosing the halide and the overall Grignard formation. We can follow that analytically. Organic reactions with online mass spec, and again, something that more people are doing. Michael addition, reaction phenylethylamine with acrylonitrile and ethanol. So we want to find this main product. The problem is that we get this particular side reactant forming, and we don't want that. So you can very easily follow that membrane-based approach using mass spec. And again, you're looking at the relative areas under the curves and following the reaction. Sulfuric acid alkylation with NMR. Again, you're alkylating following your isobutane olefin ratio. Low-cost feed, preference into higher-cost feed, and looking for propane recovery. So again, very simple process to look at that. Fourier transform near infrared, another in biochemical processing being used. Esterification of salicylic acid with acetic anhydride and using infrared again to follow that, near infrared. So microreactors are another thing that have been coming into vogue and allowing, again, us to do things that we haven't been able to do, particularly around exothermic reactions, very rapid reactions and handling that. And these are some of the benefits that we get out of process analytical technologies. Flexibility, throughput and recycle time, operational safety. This is one of the biggest benefits that we get. Product quality, because we have greater control over what's actually happening in the reactor, and achieving the statistical process control. So again, much more than just online measurements. Product quality and process performance by design. Again, certainly in the context of the pharmaceutical industry, this is a big push. Fundamental understanding of what are the underlying drivers in the process. Development of continuous processing. So batch processes by nature are inherently inefficient. And everyone has been pursuing continuous processing, but what I would tell you is that not all continuous processing is efficient as batch chemical operations. Again, it depends. So you really have to do the analysis. Facilitation of continuous improvement and quality by design. They're the really important parts. So that's a very much of a whirlwind trip through real-time analysis and how it gets used and why it's important. Any questions?